So this video is on dipole-dipole interactions and hydrogen bonding, which are two stronger IMFs. But I think I'm going to just start by quickly reviewing the London dispersion forces, because this graph can be used to show all three of them and how they interact with each other. It's a great graph. Now, the y-axis on this graph is the boiling point, and the x-axis is the period of the center of the atom that's not hydrogen. So all these compounds contain another non-metal or transition metal and hydrogen. They're all molecular substances containing covalent bonds. Now, what you want to see is you see this pattern. Now, first of all three of these substances on the bottom row that I've circled are all nonpolar symmetric molecules. I'm going to remind you because this showed up in the exam, so hopefully people will watch this video. Again, all four things around the central atom have to be the same. If you had CH3Cl, that would be a polar molecule, and therefore we'd have to talk about other intermolecular forces of attraction. But these guys are all nonpolar, so the only thing they have is London dispersion forces. And so I can do this quick review of, okay, why does SNH4 have the higher boiling point? Well, it's got a larger molecular weight, and therefore has more electrons, and therefore is more polarizable, and therefore the molecules are just stickier, okay, when they do form those temporary asymmetric distributions of electrons. Now, all the other molecules on this page are polar molecules. And let's just talk about them. Now, I've cut off the edge of the graph for a reason here, because I don't want to focus on that right now. I want you to look at the other molecules. So here, I'm going to look at, let's say, one other row. So you have this row right here. You have H2S, H2Te, and H2, I put them in the wrong order, SC. I'm really sorry about that. So I'm not going to read, I'll redo them real quick. All right, so make that SCT. So sorry about that. H2SE and H2Te. Now you see the general trend in the pattern of the boiling points as well. These three are all polar molecules. They all are bent. They all have one side that's negative, which happens to be the central atom side, because it has a higher electronegativity than hydrogen, and this side is positive. So when you see an H2S molecule, the reason why everything in this row, even though it has a lower molecular weight than the ones down here, or approximately the same molecular weight, all have higher melting points and boiling points. Because on top of the London dispersion forces, which they also have, they also have a permanent dipole. And that's all dipole-dipole interactions. H2S, H2Te, and H2Se all have one side that's positive, one side that's negative. But they also have London dispersion forces. So even though they're all very similar molecules and all have very similar permanent dipole moments, on top of that, they have different molecular weights. So even within polar molecules, you're going to see the trend. H2S, H2Se, and H2Te are all very similar. And as you can see, H2Te has the highest boiling point. Why? On top of a very similar permanent dipole, it also has the strongest molecular weight, or the highest molecular weight, and therefore is the most polarizable. So it has the strongest permanent dipole, plus it has the strongest London dispersion forces as well, because it has the greatest molecular mass. And you see this pattern all through here, right? So if I circle all the group 17s, right, HCl, HBr, and HI, I see the same pattern. These are all polar molecules, right? So an HCl molecule has one side that's negative and one that's positive, and will stick to another HCl. One side's negative and one side's positive, right? But on top of that, you see this pattern, HI, which has a far greater molecular weight, which is also a polar asymmetric molecule, also has a stronger set of London dispersion forces, and therefore the higher boiling point. So all dipole-dipole interactions are another force of attraction caused by a permanent asymmetric distribution of electrons due to the difference in electronegativities and the VSEPR geometry of the molecule, which makes it a polar molecule. So what's hydrogen bonding? Well, let's look at the graph again on the next page. All right, what I've done is I've emphasized the other side of the graph, because what you want to see is this. If you look at H2S and H2SC, right, you see this pattern. As the molecular weight increases, the boiling point goes up. you would expect to be able to extrapolate this graph to this thing and say, well, this would be where water is, right? Because water just has the same thing. It's a permanent dipole, and it's got London dispersion forces, but water molecules weigh less. So the London dispersion forces should be less. But you see an anomaly. For the elements that contain, for the compounds that contain oxygen, fluorine, and nitrogen, the pattern breaks. For CH4, the pattern continues. As the molecular weight goes down, the boiling point goes down because the London dispersion forces are weaker. So what's special about these three things that if you extrapolate these other curves, you go down here or you go down here, but it doesn't work? Well, there must be some special force of attraction in molecular substances in which oxygen, fluorine, or nitrogen is covalently bonded to a hydrogen atom within a molecule. And that's something called a hydrogen bond. Now, I'm going to very carefully define this. A hydrogen bond occurs between molecules in which H is bonded to an atom with a small radius and high electronegativity. And there are only three atoms that fit that criteria, and they are oxygen, fluorine, and nitrogen. Now, what's really important about hydrogen bonding is you recognize it doesn't happen between hydrogen atoms. So I'm going to draw the simplest one, which is water. I want you to look closely at what the hydrogen bond is. And it's not between hydrogen. Those hydrogen molecules do not hydrogen bond with other hydrogen molecules. The only IMF between hydrogen molecules is London dispersion forces, because those are nonpolar molecules. And for a hydrogen bond to occur, there have to be these three elements on the scene. So let's take a look at why hydrogen bonding occurs between water. And the way I always view this is like it's a hydrogen sandwich. And then we're going to look at it in some macromolecules like DNA and protein. So you see it again. So here's a water molecule, and here's another adjacent water molecule. Now, what's the hydrogen bond? Well, here we have the negative of the hydrogen, the negative of the oxygen, the positive of the hydrogen. It is between the hydrogen on one molecule that is covalently bonded to either oxygen, nitrogen, or fluorine, and the oxygen on the other molecule. And that's the hydrogen bond. The hydrogen bond, basically, you want to view as almost a hydrogen sandwich in which oxygens, fluorines, and nitrogens are like the bread, and the hydrogen is like the peanut butter in the middle of the sandwich, right? So here's one oxygen, here's one oxygen, here's the hydrogen in the middle. And the hydrogen is going to be covalently bonded to one of those guys, and there's going to be a dashy line with the other one. Here, take a look at this in DNA so you get a good picture of it. So these are the A's, the T's, and the G's, and the C's. And basically, in a molecule of DNA, right, these are on the two strands. So the thymine in one strand is hydrogen bonded to the adenine on the second strand. Now watch the hydrogen bond and look at the hydrogen. See this hydrogen here? It is covalently bonded to this nitrogen here, okay? And it is attracted to this oxygen in an adjacent molecule. It doesn't even have to be the same N or O, right? The hydrogen just has to be covalently bonded to nitrogen or oxygen or fluorine. And you're not going to see fluorine in DNA because there's no fluorine in DNA, right? The only time you really see hydrogen bonding and bonding fluorine is in inorganic molecules or between like molecules of hydrofluoric acid, right? So in Regents chemistry, all you had to know was hydrofluoric acid, ammonia, and water, and that got you through all the questions. So teachers, myself included, don't spend a lot of time in this, but it's really important in biological molecules, right? So here's another hydrogen bond. See the N? Here's the N and the H. They're covalently bonded to each other, and here's the N on the adjacent, adenine. Now, guanines and cytosines make three hydrogen bonds. And again, notice the pattern. Hydrogen sandwich. N covalently bonded to H, dash, dash, dash to an O. The hydrogen's in the middle. The hydrogen bonds between the hydrogen and the oxygen of the guanine. And the hydrogen and the reason why is basically the small electronegative elements, nitrogen, oxygen, fluorine, pull the electrons so close that the hydrogen has a stronger partial positive charge than normal. And that's really what it's all about. Remember I said this in another video? I said, look, these partial charges vary in their strength, right? If you have a plus one, it's plus one. If you have a partial plus one, you're somewhere between 0 and plus one. In a hydrogen bond, okay, the value of that positive charge in the hydrogen might be zero point 0.1. Now you might say that's really small, but compared to a normal dipole, which is like 0.01, it's 10 orders of magnitude greater, and it's closer to being the charge in an ion. And that's why these IMFs are very strong. So over here, you again have the NH, and then you have the N over here. And again, the partial positive on this hydrogen is a relatively strong partial positive, and that's why the hydrogen bond is a relatively strong IMF. So the bottom line is hydrogen bonds tend to be stronger IMFs, and they often ask questions like this. So I wanted to point this out. Like, if you were to compare the strength of the IMF of, let's say, methanol, and there's a good video on this, which unfortunately I'm not going to show you. Ethanol, which has two hydroxides, versus glycerol, right? And by the way, glycerol is often something they use to dilute isopropyl alcohol in this time of coronavirus, and it's what makes the hand sanitizer so gelatinous, or they use propylene glycol. If you have more of these hydroxyl groups on here, these OHs, then you can make more hydrogen bonds, and so the IMFs are stronger. So it's not even just, can you do it? It's, okay, how many hydrogen bonds can you form for a small molecule? And this is called glycerol, which is a trihydroxyl alcohol. And because of the fact that it has three of these hydroxides, if you put your hands into it, it literally feels almost like ketchup. Okay, it's so viscous from the strength of the IMFs, right? And of course, the bond would be like, here's the three C's, here's the OH, and an adjacent molecule. And by the way, these would all have angles to them of like 109.5. There'd be another, glycerol molecule right here, and its hydrogen would be, its OH would be like this, and the H would be sticking to there, and this one to that. And so there'd be all these interactions between the O's and the H's between the molecules, and again, the more hydroxyls you have in there, or the more amine groups you have on something, like those nitrogenous bases we saw earlier, right? By the way, hydrogen bonding pretty much occurs in just about every acid. That's in all oxyacids, because all oxyacids, the hydrogens are always connected to the oxygens. So I know I'm kind of going on here, but like, you had a problem where you had to figure out the structure of, let's say, a hydrogen sulfide ion or sulfuric acid, right? So in sulfuric acid, those two H's are both connected to the O's, meaning sulfuric acid can hydrogen bond. And this, by the way, also explains why all acids are soluble in water. They are polar molecules, and all the oxyacids are capable of hydrogen bonding with water as well. Hydrogen bonding is super important. I wish I could spend another 20 minutes on it.